This is Science Max, Experiments at Large. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferro-fluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max, Experiments at Large. Greetings, Science Maximites. My name is Phil, and welcome to Science Max, Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet. You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction. And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together. Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch. And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Centre. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out. And after we're done, I'll need to come back and clean up the giant mess I made in the lab. Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh, via the portal?
Yeah, by the portal.
Oh, okay.
You sure? I know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay. Don't worry about it.
No, I think
It's
definitely.
fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on And it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You could also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery,
Yes.
more voltage, and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet, and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we were not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but.
No, but bring it closer and.
Oh yeah, look at that. Okay, we
Not
turn
bad.
it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have
Yeah.
old appliances around?
I have parts bins with a whole bunch of stuff. Maybe
Oh.
we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right. Pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here. And if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So now let's max it out. Haha, a D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and haha, it spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's,
Here.
I can't pull that off. Okay, wait, grab this. Okay,
Work together.
yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is
What
there
do
a way
we?
to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo, and prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh,
Is that a magnet?
this? No.
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just for...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks, because I will knock them off with my magic. You will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you.
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight,
It held 100 kilograms.
Oh.
which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got,
2 electromagnets, 1, 2.
and those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
that's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes a lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready, let's do it.
Okay.
Oh my goodness. What?
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets! You wanna go?
No,
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha. There are two. Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. Whee! But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put 2 around a pencil, and then 4 more in such a position that you can put the pencil against this wood on the side, and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate meat. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No. But how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnets sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, that is definitely attached to the floor. Thank you. All right, now, if I just get this lined up, oh, look at that. It could totally, oh, wait a minute. Totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And, am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science!
Turns out trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this But actually, the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan.
Okay. Board,
Magnets.
magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws, or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet me. I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it, nothing unusual happens. But watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science.
So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy.
And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear, no, that's okay. I can fix this. If I just maybe, maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, experiments at large, and we'll see you again as soon as we get into the camera.
Science Max! On this episode of Science Max, I'm on a quest to harness the power of lightning. Its balloon-sticking, hoop-levitating, hair-raising power is all thanks to static electricity. Hold on to your grounding rods. There's electricity in the air. All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Welcome to Science Max, experiments at large. My name is Phil, and today on Science Max, we're going to be harnessing the awesome power of lightning. How are we harnessing the power of lightning, you ask? With this balloon. I know what you're thinking. You're thinking, Phil, what's similar between a balloon and lightning? Well, nothing right now. But behold, as I use the power of static electricity and rub the balloon on my head. Because basically that's how it starts. You see, when I rub this balloon on my head, it's stealing electrons from me, creating a positive charge in my hair and a negative charge in the balloon. And the interesting thing is, you know that things with opposite charges attract each other, right? Something that has a positive charge will attract negative things and vice versa. But anything with a charge will attract anything with a neutral charge. See all these things on the table? They all have a neutral charge, which means they've got equal amounts of positive and negative. Right now, this balloon is building up a big negative charge, which means it will be attracted to all of these things. This can of Science Max soda, it has a neutral charge. The balloon has a negative charge, which means the can will be attracted to the balloon. And this paper is neutrally charged, which means the paper will be attracted to the balloon. And if you hold the negatively charged balloon next to neutrally charged sugar, haha, sugar storm. And you probably, wait, I don't want to get sugar in my hair. And you probably know this trick. If you rub a balloon on your head, you can stick it on the wall. Ha-ha! But what does any of this have to do with lightning? Well, the same thing is going on with a lightning bolt. The clouds become negatively charged, and that negative charge wants to equalize itself with the ground, which is neutrally charged. And that lightning bolt is the electricity jumping from one place to another. And you can see this yourself. If you rub a balloon on your head and you put it next to something metal, like a doorknob, there'll be a spark. But here's another thing you can do if you don't have a balloon, which I guess I don't anymore. Rub your feet, if you're wearing socks, on a carpet, and then turn out all the lights and touch a doorknob. You might be able to see a spark jump from your finger to the door. That's lightning in a very, very small form. So that's what we want to do today on Science Max Experiments at Large. Max out lightning! I think I'm going to go to the Ontario Science Centre and ask Heather her advice. She really knows her stuff. I'm going to go see if she's busy right now. Come on.
Bill, you got the portal fixed, though.
Well, it's not exactly fixed. It's still got a couple bugs that I'm ironing out, but I stopped coming in 10 feet above the floor.
Hey.
So that's a step in the right direction. Anyway, Heather, I've come here because I want to ask your advice on something.
Yeah, for sure.
Awesome. So what I am doing is creating lightning. So this is where I'm at right now. So this is a balloon. I blow up the balloon, and then I rub it on my head, and it creates a static charge, right?
Right, yeah.
Just like in the lightning bolt between the clouds and the ground.
And the ground.
So I was wondering if you could help me maybe max that out, and I thought the perfect place to start would be a larger balloon.
Ooh, right on. Actually, yeah, I like this.
Yeah.
I've got a big balloon, if you just give me a second.
Sure.
All right, catch.
Okay. All right, giant balloon. So what I figured is I'll just start rubbing it on my head,
Okay.
and then we could maybe stick it to the wall or something?
Yeah, I think instead of a wall, we can even try on this whiteboard here.
Oh, okay, great.
Keep rubbing.
I'm
You're doing great.
rubbing. Okay, ready?
Yeah.
Here we
give it a
go.
try. And
So that didn't exactly
right,
work.
yeah.
Both of us rubbing our heads on the balloon.
Okay.
And go. Wow, that was a whole lot of nothing.
Well, we've got a really heavy balloon here.
And I
so-
feel like our heads are only this big, so we can't cover as much surface area of the balloon.
Fortunately, you can also build up a static charge by rubbing a balloon on a sweater. Or if your balloon is giant, rubbing sweaters on your balloon. But even that didn't work so well.
I think what we need to do is come up with a better way to create a difference of charge.
Yeah, let's forget about the balloon.
You have something else?
I have something else really awesome here at the Science Center. You want to check it out?
Yeah, absolutely.
Yeah, right.
Should we take the sweater and the balloons, or should we leave them here?
We'll leave them here.
Okay.
So here's how static electricity works. Normally, everything has equal numbers of positive and negative charges. That's when things are said to have a neutral charge. But when you rub a balloon on your head, the balloon develops more negative charge than positive because it pulls electrons from your hair. The same thing happens in clouds during a storm. The cloud develops a negative charge when water molecules start bumping into each other. A lightning bolt happens when the negative charge in the cloud gets so big, the attraction to the positive charge in the ground gets strong enough that the electrons can make the jump all the way from the cloud to the ground, and you get lightning. Heather and I tried to max out the static on a balloon, but a big heavy balloon just doesn't hold the same charge.
That didn't exactly work.
Yeah.
But we're only interested in maxing out the static charge, and Heather knows just what to use.
Wow. So this is the Ontario Science Centre
Yes.
electricity show?
Yes.
Okay, so where's the electricity part?
The one we're going to be playing with is right there.
So the giant mushroom.
Yeah, well, it does look like a mushroom.
We're gonna make some sort of electricity salad.
All right, head on up onto that platform right
Oh, okay.
there. And I need you to put one hand on that silver ball, yes. So the way it
Nothing
works...
is happening.
Patience.
Okay.
Once I turn it on, when I engage it, this is going to steal your negative charge. So it's going to steal your electrons. So if it steals electrons, you're going to be positively charged.
So it'll make me more positive.
Even more positive.
Yay! Woohoo! I am positive.
Here we go.
Woo!
This machine is called a Van de Graaff generator, and it pulls the negative charge away from the person touching it.
That is great!
Instead of having equal amounts of positive and negative charges, you become positively charged.
Woohoo! Science hair! Yeah!
Like when you try to put two positive ends of magnets next to each other, each hair on your head starts to repel the others and be repelled from your head.
Science hair! Dude!
So your hair stands up.
Yes! Woohoo! I can't see anything. So this is more of a machine to generate hair standing up, but it doesn't make lightning.
Oh, well, actually, I have a demonstration in my back pocket. This is gonna help us
Okay.
to create lightning. This is our grounding rod.
It is my scepter of science.
And so we're gonna use this to continuously provide that negative charge.
That's why it's
static.
plugged in.
That's why it's plugged into the ground, yeah.
Okay.
Okay, so then if you touch it to that metal ball, got it? Not too exciting, right? So pull away and let's see what happens.
Whoa! This is what I'm talking about.
Very good.
The Van de Graaff creates a positive charge. The rod has a neutral charge. When the difference becomes big enough, the charge jumps the gap.
Behold, I have the power of lightning! So it's the difference between the positive and the negative is what we want when we want to make a lightning bolt.
Yes.
So is there something we can use to make that happen? Large difference of charge?
Yeah, I think I have just the thing.
Oh, yeah?
Yeah, you wanna check it out?
Absolutely.
All right,
Okay, let's
do
go.
it.
So, you would like to move electricity from here to there. Well, what you need, my friend, is a conductor. All right, a little more arpeggio this time. No, not that kind of conductor. All aboard? No, not that kind of conductor either. This kind of conductor. I know what you're thinking. You're thinking, hey, that's just a piece of metal. Well, that's right. That's because you're smart. This is a circuit. Electricity flows from this battery along the wires and into the light bulb. But Sal, you cleverly observe, the light bulb is not lit. This is true. That is because we have a gap in the circuit. And air is not a good conductor of electricity. Is metal a good conductor of electricity? Let us find out. Metal is a good conductor of electricity. What about wood? Nope. What about this horseshoe? Is a good conductor. Will this sandwich conduct electricity? Nope. No. What about this plastic fish? Nope. What about this pickle? No, pickle is not a good conductor. That's why we make electrical wires out of copper and not pickles. You know, in case you were wondering. Lightning bolts make interesting patterns. That's because the electricity is searching for a way to get from one side to the other. But it's hard to see the patterns of lightning bolts because they happen so fast. Fortunately, using the power of science, we can observe these patterns for ourselves in a motion we can perceive. I'm going to use electricity to recreate a lightning bolt pattern. I've got 2 nails in a piece of wood here, and I'm going to attach electrical leads to both nails. Now, the electricity wants to go from that side to that side, but it can't. It has to go through the wood, and wood is not a very good conductor of electricity. Now, this is very dangerous. I need a special machine even to pull this off, so this is definitely not something you want to try at home. In fact, I'm gonna stand way back here when I turn it on.
Like water, electricity tries to find the easiest route to get from one place to another. But sometimes that involves branching out until the right connection is made. Lightning bolts do the same thing when they branch out between the clouds and the ground. Finally, there's a spot where the branches meet and the circuit completes itself. Then the electricity follows this one path, ignoring all the others.
And there you go. We just watched a lightning bolt happen in slow motion. Haha, science.
Back to our main experiment where Heather and I are on a quest to use static electricity to recreate a lightning bolt. Our experiments with the Van de Graaff generator had some hair-raising results, but Heather has another experiment she wants to show me.
This is Jacob's ladder.
Oh, so this is another way to make lightning.
Yes.
Lightning?
We're gonna see, yeah.
Let's do it.
All right.
How do we get it to go?
All right, so we want to turn it on.
Behold! Oh, turn it on,
Not-
okay.
not-
Go!
Oh.
Ooh, look at that!
You can actually see that light climbing up between the two copper wires.
That's why you call it Jacob's ladder, because it's got the rungs of the ladder.
Yeah. Between these 2 points, there's a really great charge difference, right?
Okay, so what's the difference?
10,000 volts if you're looking at it.
10,000 volts.
Yeah.
And volts is how you measure the difference in charge.
Exactly.
Why does it go up?
So it goes up because rather than just staying at the closest point, is because we're heating up the air.
Oh,
point,
so
yeah.
hot air rises.
Hot air rises.
And it takes the electricity with it? So if we cooled the air, it wouldn't go up?
Wouldn't immediately go up, yeah.
And there it goes, and it heats back up again.
Yeah.
That's neat. Okay, so we have a Van de Graaff generator. We got a Jacob's ladder. Are there any other devices that make lightning like this?
Ooh, yeah, there's other things like the Tesla coil, really high.
I have a Tesla coil.
You have a Tesla coil?
I do. I've got one at the lab. I've just never known how to hook it up.
Oh, I can help with that. Yeah.
Really?
Yeah.
Okay, let's do it. Let's
Great.
go back to the lab.
All right. Well,
should-
yeah.
I'll turn that off. Okay.
Yeah, safety first.
Okay. By now, you're probably an expert on what happens when you rub a balloon on your head, right? The balloon becomes negatively charged, which means it will attract anything of an opposite charge, or anything positive, or anything that is neutrally charged, like, like me. Look at the hairs on my arm when I bring the balloon close. Whoa! You see, the neutral charge in my body is being attracted to the negative charge in the balloon. So if something is negatively charged, what happens if you bring something else negatively charged nearby? Well, they'll repel each other. And here's an experiment you can do to make something fly using static electricity.
You'll need a balloon, a sweater, scissors, and a plastic bag out of the thinnest plastic you can find. Fold the bag up and cut off the bottom. You don't want that part. Then cut another strip from the bag. This will give you a hoop of plastic. I find it works better if you break it and tie it again. Lie it flat and rub it with the sweater. This will give it a negative charge. You'll know you've got enough of a charge when it really wants to stick to the table.
Then take your balloon and rub the sweater on the balloon to charge it up.
Because both the balloon and the hoop have negative charges, they repel each other.
Then put them together and it will repel.
And you can get the hoop to levitate.
Ha-ha! A floating bag of static charge. But here's the thing. You need to keep it away from your body, because if you get close, the bag will stick to you, because you're neutrally charged and the bag is negatively charged. Pretty cool, right? Well, let's max it out. Maxed out floating static ring. Whoa, no. Yeah! Look out, look out! Oh, no! Oh, sorry about that. Oh well. It was fun while it lasted. I gotta charge these up again.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. I didn't see you there. My name is Buster Beaker, and welcome to Cooking with Science. Let's say, for example, I've spilled the salt. Oh no, look at me. I've spilled the salt. Oh, there's salt all over the place. Not really a big deal, right? All you have to do is clean up the salt, put it back in the container. But oh no, I've also spilled pepper on the salt. But that's all right. You might be able to carefully separate the salt. But no! Oh dear, look, the pepper and the salt are all mixed together. What do? Well, here's how you can save the day using the power of science. All you need is a cloth and a plastic spoon.
like this one here. Just rub the plastic spoon on a cloth, and you'll be charging it up with a negative charge of static electricity. If it's got a negative charge, it will attract anything that has a neutral charge, just like the salt and pepper. But I know what you're thinking. How will we separate them? Well, here's the answer, my friends. Pepper is lighter than salt. Observe. So if you hold the spoon high enough, the pepper will be attracted and make the jump up to the bottom of the spoon, but not the salt, as long as you've got it high enough up. Because the salt is heavier, you'd have to bring the spoon closer, which we're not going to do. And if you tap it off to the side, you'll make a nice little pile of pepper, and there you go, separating pepper from salt using the power of science. Thanks for watching Cooking with Science. I'm Buster Beaker.
Heather and I have been on a quest to recreate lightning using static electricity. We've gone from balloons to a Van de Graaff to a Jacob's ladder, each more lightning-y than the last. Finally, Heather suggests we use a
Tesla coil.
Oh, is this named after Nikola Tesla?
Yeah, he invented it.
Oh, one of the founding fathers of electricity, right? I
Right
love
on.
Nikola Tesla. He's cool. So how does it work?
So the way this works is it is a step-up transformer, meaning we take a lower voltage and bring it up and ramp it up to a much higher voltage.
Okay, so normal voltage is 120 volts. That's what we have a normal plug-in
Typically,
socket.
we're getting it out of, yeah, exactly. And we're gonna ramp that up to really high amounts, upwards of 25,000, maybe even 250,000.
Wow.
Volts.
That's a lot.
And all that charge buildup, we're gonna see something pretty amazing happen.
Okay.
Do you wanna see it?
Yes, we stand back there, right?
Let's check it out. And
The Tesla coil builds up a charge which jumps through the air to this neutral rod, just like a lightning bolt.
We made a lightning bolt! That totally jumped a long way. That was impressive.
that was a really good one.
So can you control it?
Yeah.
Okay, show me.
You wanna see? All right. I'm going to lower my frequency.
Okay.
Let's see what happens.
Oh, that's amazing. Oh, it's like a scattered lightning bolt. Oh, wait a minute. So you can play different notes?
Play different notes.
I need 5 minutes. Hold on.
Okay?
Okay. All I need is 5 minutes. You know, I was thinking is if you can make different, hold that for a second. If you can make different frequencies, that means you can make different notes, right?
Right.
So I don't need that either. Hold on. That's not what I needed. Okay, one more thing. Can I get that hammer? Yeah. Okay, ready to go.
So what is this?
When you told me the Tesla coil could play different frequencies, I thought we could make different notes come out of the Tesla coil, so I programmed it to play the notes of the Science Max theme song.
What?
Yeah! You wanna hear?
Yeah.
Let's try it. Yeah! Science Max, experiments at large, lightning bolts!
Lightning!
We have created lightning!